Welcome back. In today's lecture, I am going to talk about the invariance principle. Okay. So first of all, we are trying to understand the need of the invariance principle. Okay. So I have already discussed that whatever Lyapunov conditions, that is just a sufficient condition. What does it mean? That suppose if Lyapunov condition for the stability, either stability or asymptotic stability, if somehow that is not satisfied, it doesn't mean that equilibrium point is not stable or not asymptotic stable. What one can only say that we have to develop some new Lyapunov function, because with respect to previous Lyapunov function what we have developed for the analysis, that is not able to quantify the stability of the equilibrium point. Okay, but failure doesn't mean that equilibrium point is not stable or asymptotic stable. Okay, so what we have to do, we have to change the Lyapunov function, or we have to add some more idea, or we have to do further investigation to tell that either that particular Lyapunov, using that particular Lyapunov function, my equilibrium point is a stable or asymptotic stable, or we have to completely develop new kind of Lyapunov function. So in previous class, what we found that using variable gradient method, one can develop Lyapunov function at least for second order or third order system. Okay, so suppose that if you have developed some kind of Lyapunov function based on energy principle, and using that Lyapunov function you are not able to conclude about the stability or asymptotic stability, or in some time it might possible you are able to comment about the stability, but you are knowing that equilibrium point is asymptotic stable, but you are unable to do that kind of, or unable to reach to the calculation conclusion using that particular Lyapunov function, then it is possible to change that Lyapunov function using variable gradient method. Okay, second approach, that is called invariance principle, that you can use the same Lyapunov function, and after that you can use some kind of further analysis to quantify that if equilibrium point is at least stable, then how to add some more theory such that I can conclude that equilibrium point is also asymptotic stable. And LaSalle's invariance principle is actually based on that particular idea, and in today's lecture I am going to discuss about that particular invariance principle only. Okay, so let us start with some kind of example. So we have already seen this example. In this example I am going to talk about pendulum system where friction is involved. Okay, and we know that if I have some kind of pendulum system and if friction is involved here, then what happens, that if you give a small perturbation and after that you can remove that force or perturbation, then due to presence of friction force, finally what we can expect, that this particular displacement or whatever theta or angle displacement comes into picture, that is diode. It means that equilibrium should be asymptotically stable. Okay, if there is no friction, then I cannot comment about this. I can just tell that if you give some perturbation, then this particular pendulum is oscillate with some frequency, and that remains the same. Okay, because there is no friction force. But here we have friction force, and due to that reason we expect that finally this pendulum is going to stop at the equilibrium point, lower equilibrium point. Okay, so now we are going to conclude this kind of phenomena using the help of Lyapunov function. Okay, so what I have done here, you can see that x1 dot equal to x2 and x2 dot equal to a sin x1 minus b x2. Here I haven't selected a and b. precisely based on M, L or K. K is the friction coefficient. So now you are already knowing, due to that reason I have replaced by some constant A and B, and after that I have defined the energy. Okay, energy is the combination of potential energy and kinetic energy. So this is not exact energy, that is energy like function. Okay, because Lyapunov theory is little more flexible than the energy. They are telling that you can able to generate some kind of energy like function, and it is not difficult to check that this is positive definite function. Okay, now if you take v dot x, what we found that here I have bx2 square, x1 is missing here, nowhere x1 is involved. Okay, but due to that reason, since x1 is not involved, so due to that reason I can conclude that x equal to 0, that is trivial equilibrium point. I have several equilibrium point, but for this particular position, equilibrium point can be given like x1 equal to 0 and x2 equal to 0. So we are telling that that particular equilibrium point or origin is stable, just stable, because v dot x is less than equal to 0, not strictly less than 0, because x1 is not present here. Okay, it means that v dot x is not negative definite, that is just negative semi-definite. And we already understood this fact that if vx is greater than 0 for all x not equal to 0, vx equal to 0, then 0, and if this kind of condition is satisfied, then only I can talk about the stability of the equilibrium point. I cannot able to talk about the asymptotic stability of the equilibrium point. And in order to talk asymptotic stability, I have to make sure that v dot should be less than 0 for all x not equal to 0, means strictly less than 0, or in another language we are telling that as a negative definite. So why we are unable to comment that? Because v dot x equal to 0 for all x2 equal to 0, irrespective of value of x1. It means that if you are in two-dimensional space, x1 and x2, so you can see here that x2 equal to 0 represents this whole line. Anywhere, if you are anywhere here, then that represents x2 equal to 0. So I cannot tell that if v dot x equal to 0, I am at the equilibrium point. It might possible I am anywhere in this particular line. Okay, and due to that reason, we are just able to talk about the stability. We are not able to talk about the asymptotic stability. But what happens that, however, near the origin, the solution cannot stay identically to the set x2 equal to 0. Okay, so what further people has seen that, because that is also obvious from the example, since friction force is there, so if you remains anywhere here, so this Lyapunov analysis is telling that after some large time you are going to remains on x2 equal to 0, and but it is possible to show that I cannot maintain here. Why I cannot maintain here? Because I have some kind of friction kind of force. Okay, so mathematically how to tell that I am not going to live here, means in this particular region, that is vicinity of equilibrium point. Lyapunov function is just able to tell us now that system is stable. Okay, so there is no dangerous situation, and if you start anywhere, finally you are going to converge to this line x2 equal to 0. So that kind of information I have gathered from the Lyapunov function. Okay, now but Lyapunov function is unable to tell us that v dot less than 0, means I can able to get the equilibrium point. Okay, so what we have to do, we have to again see the situation by seeing this Lyapunov function. Okay, so when x2 equal to 0, at that time we trying to see that what kind of situation I have. You can see from this equation also, if x2 equal to 0, then x1 dot equal to 0. But here what happens that if x2 equal to 0, then at that situation what happens, I have x2 dot equal to minus a signum x1. Okay, So I have x1 dot equal to 0, but x2 dot equal to minus a signum x1 is acting there. So what happens in another way, I can able to tell like this, that x2 equal to 0, it means that rate of change of the theta angular acceleration, angular velocity, that equal to 0 implies angular acceleration is also 0. Okay, so from the second equation I have x2 dot equal to minus a sine x1, and after that bx2. So you can see from here what I am telling, that now x2 equal to 0 and x2 dot also equal to 0. Due to that reason, now I have to make sure that a sine x1 equal to 0 at the same time. And if you just concentrate the motion on this line minus pi to pi, then what happens, that in order to maintain this, I have just one solution in this particular region, that is x1 equal to 0. And due to that reason, what we are telling, that the system can maintain v dot x equal to 0 condition only at the equilibrium point. Okay, so by further analysis, what we have observed, that I cannot maintain v dot x equal to 0 on x2 equal to 0 line. Okay, what happens, due to the dynamics of the system, finally v dot x0 also implies x1 tending towards 0. So x2 is already 0 and x1 tending towards 0. So both x1 and x2 tending towards 0. Okay, and this fact remains consistent with the physical phenomena, that what we are telling, that energy cannot remain constant while the system is in motion. Why? Because we have some kind of friction force. Okay, so now based on this particular example, this particular motivational example, LaSalle's has extended the idea. So idea is the very simple. If we can establish no trajectory can stay identically at the point where v dot x equal to 0, because whenever we are going to take some kind of Lyapunov function vx, that is positive definite Lyapunov function, and if we are going to conclude v dot x less than equal to 0, at that time it might possible I have some kind of set where vx equal to 0, and if we are able to show that v dot x equal to 0 only at the equilibrium point, then what happens, all solution is going to converge to the equilibrium point. So up to here I will do as usual way, and after that what we will do, we will identify what kind of point inside this set v dot x equal to 0, and we are going to substitute that point inside the original differential equation or original dynamical system, and after that we are going to see the behavior. Okay, so now I have to do extra analysis. So I have to check two algebraic equation. From the algebraic equation I can generate some kind of set, and after that I am going to put that set inside the original differential equation and try to see the behavior. Okay, so in this two stage I am going to talk about the stability or asymptotic stability of the equilibrium point. Okay, so what I mean to say now, that if you develop some kind of energy function and where v dot x, you can see that is only less than equal to 0, means negative semi-definite, then using that kind of function, is it possible to talk about asymptotic stability? So LaSalle's theorem is telling that yes, it is possible. Okay, Lyapunov original theorem is telling that is not possible. You have to change the Lyapunov function. But what LaSalle's is telling, there is no need to change the Lyapunov function. You can just add the extra analysis. Okay, so what happens, that using negative semi-definite function I can talk about the asymptotic stability. That is not obvious from the Lyapunov analysis. Up to here anyone has confusion, then please let me know. Have you understood the idea? Silpi, are you here? So any confusion in idea? Have you understood the idea?
Yes, sir.
Baby Dina, Iram, anyone has confusion? So if you understood the idea, now what we are going to just do, we are just going to drive some kind of extra condition, how to generate this set. That is now that is just the other extension. Okay, so idea is pretty simple. You can take any Lyapunov function, and suppose derivative of Lyapunov function is negative semi-definite. Now you can add extra analysis such that you are able to show that phi dot x equal to 0 only at the required point, means equilibrium point. If you are able to do so, then I can talk about the asymptotic stability. In some case, I can also able to talk about global asymptotic stability if Vx is radially unbounded. Okay, so just by seeing the rate of change of Lyapunov function, if that is negative semi-definite, then I can talk about the asymptotic stability. That is the basic idea of the LaSalle's invariance principle. Okay, if up to here anyone has confusion, then please let me know. Okay, now what I am going to do, I am going to first state some kind of definition to support this idea, and after that we are going to see that what kind of extra benefit. So one benefit is obvious, that I will start with any Lyapunov function, and after that I will check the rate of change of that Lyapunov function. Even if that is semi-definite, I can talk about the asymptotic stability. Okay, parallelly we are going to try to see that what another kind of benefit basically comes into picture if I believe on the invariance principle or the LaSalle's invariance principle. So some definitions are required. So first definition is about the positive limit set. Okay, so definition is not so difficult to understand. So what definition of positive limit set is telling, suppose xt is the solution of some autonomous differential equation x dot equal to fx, and a point p is the positive limit set of x if there is a sequence tn, and if I have, using this sequence, I can able to give guarantee that as tn, so tn as n tending towards infinity, tn tending towards infinity, xtn tending towards p as n tending towards infinity. Okay, so it means that I have some solution, and what I am going to see, I am going to see the futuristic value of the solution. So each time I am going to see the progress of the solution. So if p is the positive limit set, then that solution xt is tending towards that p. Okay, that is the meaning of this particular definition. So I am assuming that here I have point, and most of time if you see the equilibrium point x dot equal to fx, then that will satisfy this kind of property. Okay, so property of positive limit set. But what we found when we are dealing with the limit cycle, at that time it might possible that I have more than one equilibrium point, and all equilibrium point is also connected. So we have connected equilibrium point. Okay, so isolated equilibrium point, that is fine. I have some kind of point set kind of positive limit point kind of situation. It might possible I have several equilibrium point that might be connected, not connected, that doesn't matter for us. So due to that reason, next definition is required. This set of all positive limit point of xt is called the positive limit set xt and denoted by L plus. Okay, so if now remark is that if xt approach asymptotically to the stable equilibrium point x bar, then x bar is the positive limit point of xt, and that is denoted by L plus x bar. Okay, so whenever we are talking about asymptotic stability, we are just going to talk about the positive limit point. Okay, similarly if we are talking about a stable limit cycle, at that time we are going to talk about the positive limit set, because whenever we are talking about the limit cycle, what we found that if I have some kind of system where locally this is unstable but globally it is stable, you can see that. So locally what happens, all trajectory whatever that is starting in the neighborhood of equilibrium, that is diverging, but at the large distance they are converging towards this point. So this point is called limit set. So and once you start from anywhere inside this set, you are not going to leave. Okay, so due to that reason, this has some kind of property like the stability, that if you are trapped somewhere, then you are going to only leave, or it might possible you can move in this particular orbit, but you are not going to leave that orbit. Okay, so a stable limit cycle is the positive limit set. That is not a point, that is set, because I have several points here of every solution starting sufficiently near to the limit cycle. What does it mean? That if you start nearby of the limit cycle, you are going to converge there. That is the meaning. And invariant sets I have already defined about the invariant set, but here just for the completion I am going to give the again I am going to define it. So invariant set is a set M is an invariant set with respect to x dot equal to fx if x0 initial condition belongs to M, implies xt all futuristic trajectory, if that is going to belongs to M, then we are telling that as a invariant set. Okay, and obviously equilibrium point and limit cycle both are invariant set. Why that is invariant set? Anyone can comment about this? Anyone?
So, because if we are going to start from that point, we are going to leave.
Yeah, we are going to leave there. Okay, and due to that reason, that is invariant set. Okay, now what we are going to see? We are going to see one more point, that is the positive invariant set, positively invariant set. So, so just now we have seen the definition. Here you can see that inside definition they are telling that for all t belongs to R. So R is set of real number, that is positive, negative. So so it means that means if we are at equilibrium point, I cannot distinguishing the time that we are in future we are moving in future direction or past direction. We are just telling that it might possible in past, if we are in equilibrium point, I do not know that where we are. Okay, so it means that if we are on equilibrium point, I can tell that it might possible from the past onward or in all future I am going to live there. Okay, I am not distinguishing between negative and positive. But here you can see that whenever we are talking about positively invariant set, at that time I am going to distinguish it. I am telling that for all futuristic time t greater than equal to 0, a set M is positively invariant invariant set with respect to x dot equal to fx if x0 belongs to M, implies xt belongs to M. It means that I am just worrying about the future. I do not know what kind of things happens to past. Okay, are you able to distinguish between these two, positive invariant set and invariant set? In invariant set, positively invariant set, just we concern about our futuristic trajectory. Okay, we are not worrying about any past kind of things. Okay, so now if you see the Lyapunov set, we have already proved this. This is positively invariant. So here this set is positively invariant. It means that if you trap inside this set Vx less than equal to C and V dot x less than equal to 0, then you are not going to leave this set. Okay, anyone has confusion? We have already proved this also. Now another point, another definition that is required, that distance from a point P to set. Okay, I have certain kind of point and suppose I have set. So set have infinite point, then how to measure the distance from point to set? Okay, so distance from the point to set is defined like, you can take any norm. Okay, either you can take 2 norm, infinity norm, 1 norm, that doesn't matter, and you have to select infimum. Infimum value means minimum of all distance between P to X. Okay, so now what you can do, suppose this is M is the set. So I inside set I have infinite many point. What we are going to do, we are going to select the closest distance. Okay, that is the distance from P to this point to M. In that way we are defining this. So what we are telling, that xt approaches a set M as t approaches infinity, if for every epsilon greater than 0 there exists a t such that this condition is satisfied. Okay, so what we are telling that xt, this trajectory is approaches to set a set m as t tending towards infinity if this kind of condition is satisfied. So this is just a attractivity condition. We are telling that this distance is going to minimize. You can start anywhere, then you are going to converge to this set. So how to make sure? One can do, so using this definition it is possible to show. So you can check for all t greater than or equal to t, and if distance is less than epsilon, then I can tell that xt approaches towards that particular set xt. Okay, so first what happens, that I have given some initial condition, so that is a point. Now I am telling that that point is going to converge to some set. Okay, so how to do that, how to tell that that is going to converge to this set? Every time I have to check the distance. If distance is decreasing, then I can tell that that is going to converge to that particular set. So this definition is basically telling the same. Now what I am going to tell that every solution xt starting sufficiently near a stable limit cycle approaches the limit cycle as t tending towards infinity. What I mean to say, that you try to see that I have limit cycle. So if you have given initial condition here, so at some time t0 I have just one initial condition. Okay, some unique initial condition is selected by user. Then what happens, this is my equilibrium point. So what happens, that if you are selected equilibrium point here, then corresponding to this I have point, and this whole thing is nothing but some kind of set. Okay, so now what happens, that if this is stable, then finally I converge to this, like this, something like this. Okay, so every solution xt starting sufficiently near a stable limit cycle approaches to limit cycle. So that is the example of the previous definition, that what happens, that distance from a point p to set m. And why we have defined this kind of distance, you try to see that, try to understand that what we have seen in the motivational example. During motivational example, what we found, that v dot that is less than equal to 0. So v dot less than equal to 0, there exists some kind of set where v dot equal to 0. Okay, now what we are telling, that whenever we are inside this particular set, whenever we start anywhere, then is it possible to converge to this particular set or not? So that kind of condition basically given by this v dot less than equal to 0. So if v dot less than equal to 0, then I can give guarantee that any point, if I start anywhere, finally I will converge to this set. Anyone has confusion on this point, then please let me know. So somehow I will take some point, and after that checking the distance from that point to this particular set, v dot equal to 0, that is set in previous example, if you remember, then that will give set like x2 equal to 0 and x1 not equal to 0. So that is not a point, this is a whole set. Okay, now if I will take any initial condition equal to 5 and 2, suppose x1 equal to 5 and x2 equal to 2. So finally I converge to this set. So I have to check the distance between these two, and if that will satisfy this kind of condition, then only I can tell that what happens, that convergence happens, and due to that reason I have defined the distance from point to this set, and this example is given. One more important point, however, xt doesn't converge to any specific point on the limit cycle. So because what happens, that whenever we are talking about a specific point, then we are telling that there exists a limit, but here you can see that limit doesn't exist. What happens, that we are just able to tell that converge, and where still inside this cycle they are moving. So I am not telling that will converge to this point. It might possible they will converge anywhere. Okay, so whenever we are talking about the convergence of one point, some point to some kind of set, at that time we are not telling that this whole set is some kind of limit point. Anyone has confusion, then please let me know. Limit means if some limit occur here, then you can start anywhere, you are going to converge there, but that is not the situation. We are just telling that okay, if you are very insufficient vicinity of this, then you will converge and you are going to maintain there, you are not going to leave there. Okay, but limit is telling that you can exactly converge to that point. Okay, so whatever set I have created by v dot equal to v dot equal to 0, you might have seen in previous example that they are going to maintain inside this set and finally they will converge to the largest invariant set, that is equilibrium point. Okay, that is also limit point. Anyone has confusion on this point, then please let me know. Binay, are you able to understand this point, what I am sharing? Okay, now what up to now here we have established several definition. So several definition means positive limit point, positive limit set, invariant set, positively invariant set, and distance from set to distance from point to set. So we have specified this kind of terminology. Now actually next theorem is going to relate all terminology. Okay, so actually proof is very much involved and lot of extra theme is required in proof. Due to that reason I skip this proof. Okay, let us just try to understand the statement of proof, and once you become mature then you are able to understand this proof also. So what we are telling that if a solution xt of x dot equal to fx is bounded, okay, what we are telling that this solution xt is bounded, okay, and belongs to D for t greater than equal to 0, then its positive limit set L plus is non-empty, compact and invariant set. Okay, so what we are telling that suppose I have some kind of autonomous equation I have taken, and in this particular autonomous equation I have some solution, and if I know that solution is going to evolve inside some bounded region D, then always it is possible to show that positive limit set means when this solution is going to converge some point, they are always exist. Non-empty means they are always exist. Okay, compact means that is closed and bounded. Okay, so closed is required because we are whenever we are talking about the closed means we are talking about the sequence, and we have already seen that since xt is going to converge to L plus positive limit set, due to that reason sequence is required, and due to that reason we have imposed this kind of condition, compactness condition. Boundedness is already there, so boundedness plus convergence, that implies the compact. Anyone has confusion? And invariant set is required because we are telling that it might possible xt is going to converge to some kind of set or some kind of point, that doesn't matter for us. Okay, so a solution xt of x dot equal to fx bounded and belongs to D for all t greater than equal to 0. So since solution inside only a region, and due to that region I can tell that, and that region is bounded, so whatever limit set I am not talking about limit point, I am talking about limit set, is non-empty, compact and invariant. Okay, and moreover xt approach towards L plus as t tending towards the infinity. Okay, so idea is very simple, that if I will see the all solution and solution is going to lie in bounded region, most of time if you see practical system that will satisfy this kind of condition, then L plus means where solution is going to converge. Okay, so that is not a point, it might possible that is set of the point. Okay, so it is possible to show that as t tending towards infinity, that solution is going to converge to that particular set, and after that they are not going to evolve. Otherwise solution never remains bounded. Okay, up to here any confusion? Now if you believe on this particular lemma, then now I am going to talk about the LaSalle's invariance theorem. So what LaSalle's invariance theorem is telling, let fx be a locally Lipschitz function, and that is required because x dot equal to fx is my system, autonomous system, and I want to know that solution exists. So for existence of solution, this is required. Define over a domain D, and I know that if I have some kind of compact set, then always, because we have seen three different theorems, that if fx is locally Lipschitz, then local solution exists. Fx is globally Lipschitz, then global solution exists. If fx is locally Lipschitz in some domain, compact domain D, then there exists some kind of unique solution. So similar kind of things I am going to impose using this theorem. Let fx be a locally Lipschitz function, define over a domain this, and I am going to talk about some set omega that belongs to D be a compact set that is positively invariant. Compact set means if I start, solution is going to start from this omega, that is going to live inside the omega with respect to this we are telling. That means whatever solution, so solution is generated from this, and I am assuming that that solution remains inside this. Okay, so since fx is locally Lipschitz, so always I can give that there exists a unique solution for all t greater than equal to t0 for this inside this compact set. Okay, that is just from the existence and uniqueness of theorem. Now what we are telling, that now suppose Vx be a continuously differentiable function over D. Okay, please be careful here. I am telling that Vx is a continuously differentiable function, but I am not telling that Vx is a positive definite continuously differentiable function. Okay, so here I am relaxing one thing, that Vx, I am just telling that okay, I can take any kind of Vx, and just I have to make sure that v dot x less than equal to 0 in that particular compact domain. Okay, so here one relaxation comes into picture, that whenever you are going to apply LaSalle's invariance principle, then you have to select some kind of compact set, positively invariant compact set omega, but Vx might be positive definite or might not be. Okay, after that we are telling that let E be the largest, E be the set of all point in omega where v dot x equal to 0. Okay, so actually from motivational example, what we found that Vx I have taken that is always positive definite, and v dot less than equal to 0. Okay, so here LaSalle's theorem is relaxing that Vx that is positive definite, but they are maintaining v dot x less than equal to 0, and v dot x less than 0, they are assuming that there exists a compact set, because when Vx is positive definite and v dot x less than equal to 0, then we are able to prove that whatever set that comes into picture using the Lyapunov fundamental theorem, you have already seen that is nothing but compact set. So here they are assuming some I have compact set, and due to that reason v dot x positive definiteness is not required. Okay, now let E be the set of all point in sigma where v dot x equal to 0, and now whenever we are telling that v dot x equal to 0, it means that I have several points inside that set. In that previous example, what we found that x2 equal to 0 and x1 not equal to 0 is v dot x equal to 0. So I have set of points. So that set of point I am going to represent using this set E, and M is the largest invariant set. Largest invariant set means all trajectory finally going to converge to that set. Okay, so that is called largest invariant set inside the M. So what is largest invariant set in case of the motivational example? Anyone can comment? So in the previous example, what we found that I have two-dimensional system, and after equating v dot x equal to 0,
So then x1 equals to 0.
yeah, x1 equal to 0. So E equal to 0, and how to create E set E? Set E I can create v dot x equal to 0. So set E is x2 equal to 0 and x1 not equal to 0.
Not equal to 0.
And largest invariant set M is nothing but 0, 0, because all trajectory is going to converge to that that in that way we can identify the largest invariant set. Then every solution started in that omega approaches to m as t tending towards infinity. So what basically this theorem is telling? This theorem is just telling us like this. Okay, I will try to draw one diagram. So suppose I have some kind of system x dot equal to fx, and their mathematical model is valid in this region D, so I can plot it this region. Okay, after that what I am going to do, inside this region I will going to check some kind of compact set, and I have make that set omega. This is compact set I have selected. Okay, and since fx is locally Lipschitz inside this region, and due to that region I can tell that there exists a solution for all t greater than equal to t0 by existence and uniqueness theorem. Okay, now after that what we are telling that if I have this kind of compact set, then if inside this compact set there exists a some function vx, that is not necessarily a positive definite function. And why that is not required? Because I have already assumed there exists a omega which is already compact. Okay, so even if vx, because vx is positive definiteness of vx is required in order to show that this region compact, but I have already selected compact. Okay, so vx is here, you can see that any continuous function, continuously differentiable function, and just if v dot x less than 0, then what happens that if one trajectory started, any trajectory starting from this set, they are going to remain there. Okay, so now what I am going to do, I am going to check this condition. Whenever v dot x less than 0, it means that whatever trajectory that is going to start, that is going to decrease with respect to time. Sorry, and after that, that will converge to v dot x equal to 0. That is set E, and finally inside E, if there exists a largest invariant set, then all trajectory will converge there. Okay, so that is the idea, and same idea I am going to now state it using the proof. What we have seen that v dot x less than equal to 0 in this compact set. Okay, it means that vx is going to decrease and vx is continuous. So whenever I have some kind of continuous function inside the some bounded region or compact region, there always exists some kind of minima. Okay, and due to that region I am telling that whatever function vx, their minima is nothing but b. Okay, and what we found that vx is decreasing. Why vx is decreasing? Because now they are inside the compact set and v dot x is less than equal to 0. So due to that region that is decreasing, due to that region there exists some kind of limit point. Okay, and limit point I have assumed that is a. Now since vx is continuous and x is already continuous, and I am assuming that solution xt that inside this compact set omega, it means that and this solution is going to lie inside some kind of bounded region. So xt is bounded, and due to that region every bounded set there exists a limit point. We have already seen, so there exists a L plus in that particular region, and after that what we are telling that moreover L plus, so limit set exists, and that limit set and xt going to approach towards this limit set. So what we have seen that I have set omega and I have v dot x less than equal to 0. So finally what happens that whatever trajectory that comes into picture, then that is going to approach v dot equal to 0. Okay, and this is nothing but I have set L plus. So same kind of things I have written here, that I have limit set L plus that belongs to omega, and xt approaches to L plus as t tending towards infinity. Now if I select any point P that belongs to limit set, then there exists a time Tn with this kind of situation such that xt is going to converge to that particular point. Okay, this is true for all point inside the limit set, and after that vx is continuous. So vx is continuous, it means that I can tell that what happens that we have just seen that vx is going to converge to some point, and due to that region vx is going to converge to some point A, and we have already defined what is meaning of A here. You can see that what we have done, that as t tending towards infinity, I am telling that Lyapunov function is decreasing. but after some time they stop decreasing, they decrease to A. What does it mean? Because in previous example what we have seen that V dot is less than equal to 0. So less than equal to 0 means I have set V dot equal to 0. So once V dot equal to 0, at that time I am telling that now rate of change of energy equal to 0. So energy is not going to decrease now. From here I can only able to comment V is constant, like that. So that constant value is A, and due to that reason, and X is continuous also, and due to that reason I have written that Vx is continuous and Xtn is tending towards P. It means that solution P is nothing but that is going to tend towards the A. Okay, anyone has confusion till now? Okay, if you don't have confusion, then now things become very easy. So now since Vp is going to converge to some constant point, it means that inside that limit set L plus, so V dot X is automatically 0, because now V dot X is not decreasing. So that kind of things I have written here. So this set V dot X set is E. Okay, so what we are telling that L plus is limit set, and now limit set is basically belongs to largest invariant set, and this is belongs to some kind of invariant set where V dot X equal to 0, and that is going to lie inside the compact set. Okay, and due to that reason what we are telling that now that Xt approaches to L plus implies Xt approaches to M as t tending towards infinity, because whatever limit set that is going to lie inside the some kind of largest invariant set. Okay, so limit point or limit set is going to lie inside this largest point, and this is in the invariant set where V dot equal to 0, and here this is the largest invariant set 0 0. So what happens, that limit is finally as t tending towards infinity, that is inside this set M might be, it might possible M might be a origin or might be a some kind of line. We are going to see that using one example. Then that is not a equilibrium point, that might be a some kind of line also. Okay, so in this way one can establish the proof. Okay, so idea is pretty simple. Now in place of Vx positive definite, what you can do, you can select the some kind of Vx which is just differentiable. You can select the region which is compact where V dot X less than equal to 0. Then you can create one invariant set, and inside invariant set you can select the largest invariant set. Okay, so using example it became very easy how to select largest invariant set. Then it is possible to show that finally all trajectory is going to converge to that largest invariant set. Okay, now another theorem that is obvious consequence of the previous one. Now even if Vx is continuously differentiable and positive definite, then result remains the same. Okay, so next theorem is telling let fx be a locally Lipschitz function defined over a domain this, and origin suppose unique origin is lie inside the region of this. Initially I am not assuming that there exists a origin, okay, in LaSalle's invariance principle. Okay, but this is corollary of the LaSalle's invariance principle. They are assuming that suppose in some region I have origin is there and Vx is continuously differentiable and positive definite, and this condition is satisfied, then I can generate some kind of set S like this by V dot X equal to 0. If no solution can stay identically in S other than the trivial solution means equilibrium point Xt equal to 0, then origin is asymptotically stable. So everything remains the same like previous one, but now what we are assuming that I have equilibrium point inside the region. Previously I am not assuming that there exists a equilibrium point inside the region, but here I am assuming there exists a equilibrium point. I am assuming that Vx is positive definite also. So it is possible to show that all trajectory is going to converge to that equilibrium point. Okay, so basically whatever example I have given, that will satisfy this kind of property. I have taken Lyapunov function that is positive definite, V dot X I have created like this, and after that I am telling I know that 0 0 is going to lie inside some kind of region, and region I have already defined, x1 lie between -pi to pi and x2 may be anything. Okay, so I have some kind of region, some kind of bounded region I can create by truncating x2, then this kind of condition will hold. Okay, now it is possible to show that by this that gamma, if I will select some kind of gamma that belongs to D is a compact and positively invariant set, then it is a subset of the region of attraction. So basically how we are creating region of attraction using Lyapunov function, we are trying to identify some kind of set belongs to Rn and where Vx is bounded less than C and where V dot is basically less than equal to 0. In that way we are basically creating some kind of region of attraction. Okay, and since whenever we are applying the LaSalle's invariant principle, where we are taking the compact and positively invariant set already, so that is basically nothing but the part of the region of attraction. Automatically that becomes the part of the region of attraction. Okay, and if D equal to Rn and Vx is radially unbounded, then one can easily prove that now origin is not only locally asymptotically stable but globally asymptotically stable. Okay, so basic idea of LaSalle's is like this, that you can start with any autonomous system. Even if you do not know you have unique equilibrium point or you have origin, then how to apply Lyapunov analysis or Lyapunov kind of analysis. Okay, so both kind of things he has covered during his discovery. Okay, and due to that reason LaSalle's theorem become more famous. Okay, you can see here they are relaxing several things. What kind of relaxation comes into picture? First relaxation, that there is no need to check that V dot is less than 0 in order to characterize the asymptotic stability or global asymptotic stability. So they have relaxed the requirement of negative definiteness of the derivative. Okay, second thing, they are telling that Vx, there is no need to tell that Vx is positive definite. Okay, so you can take any Vx, just you have to make sure that Vx is continuously differentiable. Okay, so that is the second relaxation. What is third relaxation? They are telling that even if I do not know that there exists a equilibrium point, okay, it might possible if I have equilibrium set also, then also I can able to formulate the Lyapunov analysis or some kind of Lyapunov like analysis. So this theorem is basically extended the Lyapunov analysis in three different way. Okay, so negative definiteness requirement is obvious, and after that they have extended the theorem in three different way, whatever I have talked just now. Okay, let us quickly now try to see one example, that what I have done. I have taken the more generalized example of the pendulum. You can see that x1 dot equal to x2, x2 dot equal to hx1. So initially if you see the pendulum equation, so in place of hx1 I have a sin x1. Okay, and in place of h2 that is friction term, that is represented like bx2. Suppose that friction is also nonlinear. Most of time that is the nonlinear. Okay, so it means that more relevant mathematical model of the pendulum system, when friction, suppose that I have to model that pendulum system in a space, it might possible that will not follow bx2. Okay, that will satisfy some kind of requirement that I have some kind of nonlinear function with respect to x2. And now what I am assuming that is locally Lipschitz, because that requirement is there, because I am going to construct the Lyapunov function, and we have already seen that whenever I am going to apply the LaSalle's invariant principle, then fx should be locally Lipschitz. And due to that reason I have assumed that this whole two functions are locally Lipschitz. I am assuming, suppose that if I have to analyze the stability of equilibrium point, so I have to assume that hx1 and hx2 both equal to 0, and I am assuming that this kind of requirement I have y that is greater than 0 in some particular range. You can see that this will also satisfy. It is possible to show that if you take any odd function here, then that will satisfy this kind of property. And most of time whenever you are capturing the friction effect, that is represented by some kind of odd function, because friction, if you are moved in this direction, then friction force start acting in reverse direction, and due to that reason this requirement is also obvious, means practically feasible assumption is here. Now what you can do, you can take this kind of Lyapunov function. Okay, now since I have already assumed that this condition is satisfied, h1 x1 multiplied by x1, and due to that reason this is positive definite Lyapunov function, and in some particularly I have just concentrate myself in this particular region. Now what I am going to do, I am going to see the rate of change. So v dot x, if you do, then again you can see that after taking derivative of v dot x, x1 term is not present here. Okay, so I can just able to talk about negative semi-definite, and whenever negative semi-definite is there, it means that x equal to 0, which is the trivial equilibrium point, that is just a stable. Okay, now in order to show that is also asymptotic stable, what I have to do, I have to form this set. Okay, so what kind of set I can form? First I am going to form some kind of set that is called E and invariant set. So invariant, how to find invariant set? That just try to keep some kind of point where energy stop decreasing, that is v dot x equal to 0. So energy become constant. Using that I have formed this set, and it is possible to show that if you equate v dot x equal to 0, then I have x2 equal to 0. Okay, and I have already taken x2 between this range. Now it means that whatever s I have defined in the previous theorem, so that is the set where x belongs to D and x2 equal to 0. It means that x1 not equal to 0 also going to lie inside this set, and since x2 is 0, so I can also tell that x2 dot equal to 0. Now what you can do, you can put x2 equal to 0 and x2 dot equal to 0 in the original equation. So if you put x2 dot equal to 0 and x1 equal to 0 inside this equation, then I have just x2 equal to 0 in this equation, then I have just one solution hx1 equal to 0, and you see that from here assumption hi0 equal to 0, so I have only the one solution, that is hi equal to 0, and due to that reason I am telling that I have largest invariant set, that is equilibrium point, and due to that reason I have origin is asymptotically, locally asymptotically stable. Now if you see the Lyapunov function, if that is radially unbounded, then I can tell that whatever Vx I have taken, that if that is radially unbounded, and it is possible to show that if I relax this assumption y lie between minus a to any region, then that become globally asymptotically stable. Anyone has confusion on this point, then please let me know. Okay, I am going little bit fast, so if you have any confusion, then please let me know. Okay, now just please give me 5 minutes, then I will complete this session. So another example where I can apply the LaSalle's invariance principle is in order to design the adaptive control. Okay, that is very important assumption, and in case of adaptive control, it is possible to show that closed loop system, okay, closed loop system has equilibrium set, not only equilibrium point. Okay, so if I have equilibrium set, then how to talk about the stability, okay, after designing the control. So for that, LaSalle's invariance principle plays a very important role. Okay, and you can see here that I have designed control for adaptive control system. I have designed control like this. I am telling that okay, I have simple kind of control, just this is proportional control, and here I am assuming that a is not known to me, so I have y dot equal to ay plus u, and I have designed this kind of control, u equal to minus k into y. And after that you can see here that why this is adaptive, because k dot gain is also changing with respect to y, okay, where gamma is greater than 0. Now if you substitute this kind of control here, then what happens, that I have y dot equal to ay minus ky, and k is also changing with respect to time. If you take x2 as a k, means extra state variable, now I am going to consider, because k also changing with respect to time, and at that time I have second order system. So first order system is going to convert it into second order system, and now if you check the equilibrium point, so one equilibrium point is x1 equal to 0, and another equilibrium point you can see that is nothing but x2 equal to a. is also equilibrium point. So x2 equal to a means x2, this quantity might be anything, okay, because if you are keeping x1 equal to 0, then after that if you take x2 equal to a, that is anything, then also x1 dot equal to 0. So it means that x2 minus a, that is any quantity for all r, you can tell, that is the equilibrium point. Okay, so x2 is not precisely known to me. Okay, now I have to talk about stability. So I have those kind of system where equilibrium point is x1 equal to 0 and x2 is unknown. Okay, now I have to talk about the stability. I have to make sure that x1 tending towards 0, because then only I can able to solve the regulation problem or stabilization problem, you can tell. Now what I am going to do, the line x1 equal to 0 is the equilibrium set. We want to show that trajectory approach this equilibrium set as t tending towards infinity. This means that adaptive controller regulate y to 0, means I have to just worry about the one state, that is x1. Okay, so what I am going to do, I am going to design one Lyapunov function. So here you can see that I have taken half x1 square, and x2 I do not know the behavior of x2. So due to that reason I have taken x2 minus b. Okay, so in place of x2 square, since any value of x2 is also equilibrium point, so I can tell that okay, I do not know where is my equilibrium point. Due to that reason I have selected b, that is greater than a. Just in order to maintain the stability I have selected this. So any value of b that is allowed. Even if I don't know a, I can take b very, very large. Okay, so I have constructed some kind of Lyapunov function b by shifting the equilibrium point. So one equilibrium is precisely known, so half x square, and another equilibrium point I do not know. So due to that reason I have shifted x2 minus b square. Now it is possible to show that this vx is some kind of function where this is not positively definite function. Why that is not positively definite function? Because if I know precisely the equilibrium, so x equal to 0, that should be 0. That is not satisfy that kind of condition. So I have taken some kind of vx, and after that what I am going to do, I am going to take the derivative of that. If you take the derivative of that, then this kind of condition comes into picture. V dot x is x1 square b minus a less than equal to 0. Now here you can see that x2 is missing, and due to that reason, since from here I can tell that if b is not greater than a, then this v dot is not less than equal to 0. Okay, so what we have done, we have already do not assume that vx is positively definite. So I have to make sure that v dot x is less than equal to 0 in some particular region, in some compact state, that is required in order to tune the adaptive controller. Okay, so I am telling that okay, even if a do not known to me, but I can give guarantee that there always exists a b. B can be anything larger than a. Okay, so if a is finite, then b is also finite quantity more than that. Okay, so b I can define a plus 1. Okay, now since v dot x less than equal to 0, and it is possible to show that whatever v I have constructed, that is also radially unbounded. Why radially unbounded? You can take x1 tending towards infinity, x2 tending towards infinity, so vx is also tending towards the infinity. It means that whatever analysis I am going to carry, that is globally valid. Okay, now what I am going to do, that since this is radially unbounded, so if you take any vx less than equal to c, that is compact and positively invariant. Why positively invariant? Because v dot x less than equal to c due to radial unboundedness condition, and v dot x that is less than equal to 0, and due to that reason I am telling that sigma is some kind of compact set. Okay, now what I am going to do, I am going to create the invariant set. And how to create invariant set? Just you can put v dot equal to 0. So this is my invariant set, and now if you are inside this invariant set, it is possible to show that any point on line x1 equal to 0 is the equilibrium point. Why? Because I have told you that x2 equal to b. Okay, so I have x1 equal to 0, x1 0 and x2 equal to b, means any point on the b axis is my equilibrium point. It means that my largest invariant set is also the whole axis. I cannot precisely tell that only equilibrium point is largest invariant set. So any point here can be largest invariant set. Okay, so in this way I can tell that x2 is going to converge to somewhere, I don't know, and you can see that that is justified here. From control system also that is justified, because k is somehow some kind of gain. So if that gain, after whenever you are applying this control, so gain should be converged to somewhere in order to maintain the stability. So finally they are telling that okay, gain is not going to converge. If you are at equilibrium point, then that is not a problem. Even if gain is 0 and y is already 0, then that is happy. Even if that is non-zero, since y is 0, then 0 control I am apply. But during this whole analysis, what happens, gain is going to converge somewhere. Suppose that will take some value, that is b1, that is okay. Then I can apply u equal to b into y. That kind of control is applied here, and rate of change is 0. So at that time b dot is 0, it means that y equal to 0. So like that I can adopt the gain. Okay, so using this example I can also able to understand that whenever I have adaptive system, okay, then how to talk about Lyapunov stability. So Lyapunov stability is not directly applicable here. Why? Because here I have equilibrium set. Equilibrium is not a point. At that time I have to apply the extension of Lyapunov function, that is LaSalle's invariance principle. Okay, so now it is time to conclude the today's lecture. So what we found in today's lecture, that if I have some kind of system and if I have unique equilibrium point, okay, then LaSalle's invariance principle is telling then that there is no requirement of negative definiteness of the derivative of Lyapunov function. Even if that is not comes into picture, but still you can able to talk about asymptotic stability or global asymptotic stability just by seeing the behavior of the system. Okay, just by analyzing invariant set and largest invariant set. Second requirement, they are telling that Vx, there is no need to impose the condition that Vx is positive definite function. Okay, you can able to relax that assumption by taking some kind of compact region, and since lot of practical system is only evolving in compact region, so I can construct the Lyapunov function for that. After that, they are also telling that how to calculate the region of attraction, because if you are in compact set, so and Vx is less than equal to 0 and v dot x Vx is less than equal to c and v dot x is less than 0, so I can able to find the region of attraction also. So that is the second thing. Third thing is that they are telling that suppose if you have multiple equilibrium point, so I cannot apply Lyapunov analysis, okay, but I can able to apply the LaSalle's invariance principle. So due to that reason, LaSalle's invariance principle has extended Lyapunov analysis in 4 different dimensions. Okay, one dimension, that is they remove the requirement of negative definiteness, and all 3 means they are precisely able to calculate region of attraction. Second, if I have connected equilibrium point, then how to talk about stability, and the requirement of positive definiteness of Vx, that is also going to relax in this particular theorem. And due to that reason, the result of the LaSalle's are very much elegant. Okay, so with this remark I am going to end the today's lecture. Thank you very much. If you have any confusion and question, then please let me know. Anyone?